Today we're going to talk about quantum theory. And quantum theory, the first person we're going to talk about that actually coined any terms was Max Planck. And he observed that hot objects emitted light. So if you stuck a poker into a fire, a red hot poker, it would start to glow and it would emit light. He concluded that energy is emitted in small specific amounts, and these specific amounts he called quanta. Now, quantum is the minimum amount of energy needed for an energy change. So, quantum means sort of a specific amount. The next person to work on quantum theory was someone you may have heard of before, Albert Einstein. He observed something called the photoelectric effect. The photoelectric effect means that if light rays are casted on the surface of a metal, electrons are emitted from that metal. The emission of the electrons are happening because of these light rays. So Einstein decided there must be something happening here between energy and electrons, and this was the photoelectric effect. Photo means light, electric means electricity or electron emission, right? Einstein also at this time came up with a very important part of quantum theory, and this was the wave-particle duality. At the time, people were arguing whether light was more of a wave or whether light was more of a particle kind of coming through the air. Well, Einstein said it's both. It is both a wave and a particle. It has properties of both. He also came up with the word photon. Well, I don't know exactly if he was the one, but a photon is a particle of light that carries a specific quantum of energy or a specific amount of energy. So a photon kind of is going to remind us of these particles. However, we're going to talk about how the particles are very much related to the waves, which is this wave-particle duality. The mathematical relationship between a quantum of energy and frequency of the wave, frequency of the electromagnetic radiation, is E equals h nu. E stands for the energy of the light, and energy is in joules. H is a constant. It's Planck's constant, Max Planck. You can look up this number if you ever need it in your life. And nu is frequency, and that's in hertz or 1/2. So what this equation shows us, if you just kind of forget about h, you forget about that big ugly number, and you just say this is a constant and it's never going to change. What it says is that as frequency increases, because these are on opposite sides of the equation, energy also increases. As frequency decreases, energy decreases. And that's because, again, this is a constant and they're on opposite sides of the equation. So they have what's called an inverse relationship. Now, let's talk a little bit about Bohr, because we've already started, bashing him for talking about his orbits and that the orbits weren't correct. So this is the Bohr model, and you may have learned this in middle school or biology or before in your life. And the main points of the Bohr model of the atom say this. They say that electrons orbit the nucleus and that these orbits have set sizes and energy. And the energy of the orbit is related to the size. So the lowest energy is here, found in the smallest orbit, and the highest energy is found in the largest orbit. Bohr also said that radiation is absorbed or emitted when an electron moves from one orbit to another. So if an electron were to jump from a lower orbit to a higher orbit, as it fell back down, there's going to be an emission of energy. Now, this is quantum theory. Electrons only exist in orbits with specific amounts of energy called energy levels or specific energy quanta. Therefore, electrons can only gain or lose a certain amount of energy, and only certain photons, this is specific energy packet amount of light, are produced. So let's look at an electron's energy. The lowest energy state of an atom, we call this the ground state. Sometimes the electron will gain energy. Electrons can get energy from various places. They can get them from heat, electricity, other photons, and they will jump to a higher energy level. If it does this, the electron is now an excited electron. So it has to absorb enough energy to get to the higher energy level. This is often compared to the rungs of a ladder, right? You cannot go between the rungs of a ladder. Instead, you have to have enough energy to get to the next rung of the ladder. So this is, again, this quantum theory. When an excited atom returns to its ground state, or when the electron returns back down to its ground state or its lower energy level, it releases the energy it's gained, and this is in the form of a photon. We see this as visible light. So you've got an atom, nucleus, I'm not going to worry about it too much. You've got, and again, this is a model. This isn't exactly what it looks like, but you have some electron in some ground state. It gets excited and it jumps up a certain energy amount. And this excitement right here might come from, like I said, heat, electricity, other chemical reactions. But as this electron falls back down, it's going to emit a photon of light. So we're going to get something called the line-emission spectrum. Sorry, this keeps. So we're going to get something called the line-emission spectrum. So energy comes in, the electrons jump to the excited state. As they fall back down, a photon comes out. This is the most important part of this. And this line emission spectrum comes from these photons that come out. And these photons that come out are in the form of light. They are colored light, purple, blue, red, whatever the light is. And if we use a special tool called a prism or a diffraction grating, we can split this light into the different photons that have been released. So again, here's the Bohr model. You have an electron, it gets excited and jumps up, and as it falls back down, it emits light. That same electron or different electrons, we know that atoms can have several electrons, can jump a different amount, fall back down, and produce a different amount of light, or a different frequency of light, different energy of light, jump again and produce yet a different one. Notice here in my example, it jumped once, a small amount, so it has a red light that is emitted. This red light would have the lowest energy because it was the lowest jump. Then it jumped a little bit higher. It's got that green light. Green light has a little more energy than red. And then it jumped higher, and you can see here this is either blue or purple, just showing you that it has more light. I guess that was blue because here's purple. And one more thing, it can actually jump past the visible spectrum. So if this is maybe even purple, this might be ultraviolet because it might go past it. Now, the energy of the photon depends on these different energy levels, and that energy then gives us the colors that we see in the emission spectrum. Bohr calculated these energies, and he was able to only match the hydrogen atom. So if you feel like you're wondering, oh, how are we going to ever calculate this? And this seems really confusing, the energy in, and I don't know much about physics. Bohr himself could not calculate past the hydrogen atom. He was completely on the right track, but he was missing some things in his calculations. So don't feel bad. So each element has their own unique bright line. They call it a bright line emission spectrum, and we call this the atomic fingerprint. So for example, helium, every time helium lights on fire or helium is excited by electricity or a chemical reaction. Anytime the electrons inside helium get excited, as they jump, they will fall back down and they will put off this very specific atomic fingerprint, or those specific colors. Now, what do we see with our naked eye? We're going to see these colors kind of combined to one color. It would take a tool like a prism or a diffraction grating to separate it. So like I said, Bohr's calculations only worked for hydrogen. He didn't even make it to helium, which is number 2 on the periodic table. Here's some example of emission spectrums. Here's hydrogen, sodium, helium, neon as a real pretty one, and mercury. With the naked eye, they look like this. There's hydrogen, there's sodium, there's neon. I don't have helium, but you can see here, here's neon's colors, and this is what they combine to see by the naked eye. And you'll talk about this in a lab that we're going to do. And here is mercury. So again, here's what it looks like when we separate the light out through a diffraction grating, and this is what it looks like when we actually light these gases on fire. This is mercury gas that has been excited by electricity. This is a tube full of electricity that excited that mercury atom, or all of those mercury atoms. You can do the same thing, like I said, with fire. So here is sodium, and it's been put inside fire, and again, excites the electrons, and sodium glows this nice kind of yellowish color.